Hey, hi everyone. Good afternoon. Myself, Jimit, and I'll be presenting about modernizing enterprise applications with AlloyDB for PostgreSQL. A quick intro about myself. I am working here at Google as a cloud architect with our global delivery center team based out of Wrocław. And we help our customers in designing their cloud infrastructure solution around variety of use cases by leveraging various different services from Google Cloud, right? Okay, so here's a high level agenda of today's session. We'll first go through what are the key challenges so as to maintaining or modernizing your applications in general. And then we'll see what is AlloyDB for PostgreSQL and how it can help. Then we'll move on to how you can modernize your applications. And then ultimately we'll finish off with a quick demo if things go well. Yeah. So key challenges. So ask like, why do you need to, let's say, modernize enterprise applications in first place, right? So let's start with a question. What are the main challenges with maintaining your applications on day-to-day basis, which arises the need of modernization and some modernization challenges if anyone wants to pitch in? Like in general challenges of running your applications in production as such. Patching. It's like day-to-day processes, maintaining your application in general. Any other challenges? Cool. So here are some high-level challenges, right? Basically, whenever you are running your applications in production or you are maintaining them, you need to make sure about scalability. You need to make sure that they are reliable, they are easy to manage, they are accessible to the end users. You are getting real-time operational insights out of those applications. And nowadays, you need to make sure that you have AI/ML capabilities also with those applications, because organizations have growing data needs. Organizations have lots and lots of big data with them that they can leverage with AI/ML, and then they can provide better services to their end customers with variety of different use cases, right? And basically, when you start building an enterprise application as such, in general, I'm talking about, I'm shifting timeline a bit. Let's say 10 years back, if you wanted to start building an enterprise application, you had to kind of get into licensing with a database provider, choose a enterprise grade database solution, choose a legacy platform, a legacy framework, somewhere in Java, and then start building out your application. And that is when the problem started, because you end up with a big monolith that exists in your environment, in your on-prem infrastructure, that you need to maintain, manage, and now you need to figure out the whole kerfuffle around how you are going to scale that application in production and how you are going to scale that database going forward, right? And then essentially came cloud, which basically resolved that problem a bit on a high level. Like, you migrate your application on a scalable set of infrastructure and your application becomes scalable. But what about the database? The database still stays on a monolith approach, where you just migrate your database, let's say, on a virtual machine, and then you need to worry about scaling that virtual machine going forward, right? And that increases your set of problems, because let's say if you are on a enterprise database with some sort of licensing requirements, then you need to buy a dedicated machine from a cloud provider, migrate your database onto that dedicated machine. And then again, as I said, since you are migrating it on a fixed set of virtual machine, scalability is always a big problem with that kind of migration as such, because database cannot horizontally scale by default, right? You need to scale it vertically. You need to increase the number of vCPUs and RAM, and then you need to increase storage, and that has a lot of downtime if you need to accomplish all of that in a production grade enterprise application residing in a production environment, right? So we have seen this paradigm shift that developers are and enterprises are essentially choosing to move towards PostgreSQL, which is an open source enterprise grade database with rich amount of features, right? It is very developer friendly. It has lots and lots of online community presence, online documentation that is in place, and there are various different SDKs that are available out of the box to support an application to interact with a relational database as such, right? It has all the good capabilities of a relational database. You can design your schema, which is scalable, which can support millions of users, millions of queries, and whatnot. And it has out of the box support with majority of the programming languages that are out there, starting from JavaScript frameworks to Python to Java, and to any other enterprise programming languages such as .NET and whatnot as well, right? But again, if you are leveraging Postgres or any other database for that matter, that challenge still persists, which is like you need to install that on your systems. You need to maintain that even if you are running them in cloud, right? So that is where AlloyDB for PostgreSQL comes in. It was released very recently at the recent Google I/O. It is a managed database service offering which is fully PostgreSQL compatible and is suitable for top tier enterprise grade workloads in cloud. It has, like I said, it is fully compatible with PostgreSQL, so not just schema and basic queries, but it supports triggers and all of the out of the box features that PostgreSQL has to offer. So existing PostgreSQL databases can be migrated very easily to this managed service offering, and it has out of the box integration with rest of the Google services that are available within the Google Cloud Platform, right? So as we were discussing, it is as its name suggests, right? It is called AlloyDB. It's like an alloy that has been melted with all the good features that are available out there, and it has been tailored for your needs. It has the goodness of open source Postgres, and it has been fine tuned to be cloud native, to be scalable, and to support enterprise grade workloads, offer good amount of performance, and it has out of the box integration with the AI/ML services that are there within Google Cloud Platform, and it has intelligent AI/ML inbuilt within the database service offering itself. We will see that how it does that in the upcoming slides. Right? A quick bit of statistics as such. So AlloyDB for PostgreSQL has been benchmarked to be up to 4 times faster than standard PostgreSQL if you are running with the same capacity, and it grows linearly as you increase the capacity. That is, as you increase the number of vCPUs, it would grow linearly and still offer you up to 4 times more performance than the standard version. And for analytical queries, it is up to almost 100 times faster than standard PostgreSQL. And all of this basically comes from Google's experience of building enterprise grade analytical services and data warehousing services that exist in Google Cloud, that is BigQuery. It basically leverages all the goodness and technology that sits behind these services that can offer you such good performance in processing your analytical workloads. So how is it able to offer such great amount of performance than standard PostgreSQL, even though it is 100% PostgreSQL compatible, and it is basically leveraging that same open source engine underneath, right? So it starts with disaggregation of compute and storage. As we were discussing, if you are migrating a standard database into cloud, or if you are hosting and managing a database on your own, you are essentially installing that database and setting it up and configuring it on a normal virtual machine instance, right? Which basically consists of 2 major layers, that is compute and storage, right? Your compute layer essentially includes your database layer where your functions, your data, your schema resides, and it is basically stored in form of blocks on your storage layer, right? Now the problem with this approach is that if you need to scale, you need to either create a cluster by yourself and maintain that cluster going forward, or you have to scale vertically, meaning you need to add more vCPUs on the compute layer, or you need to increase your storage layer, and that includes a big amount of downtime to perform that sort of operations in a production environment, right? So here, as you can see, compute and storage layer has been disaggregated, meaning compute layer is the only layer where your actual database is residing and you are performing your operations, and storage layer has been independently residing underneath. Basically, compute layer ships the data in form of log writes to the storage layer, and then there is a log processing system that sits on the storage layer, which converts these, the data that has been shipped as logs to blocks on the storage layer, and then it is written as a block on the actual storage layer, and then replicated across multiple instances that sit within your cluster. Here's a bit more detailed diagram on how essentially AlloyDB for PostgreSQL operates and is essentially structured. So as you can see, on the compute layer, it is divided across multiple zones within the same region, meaning your compute is replicated within multiple zones within the same region for high availability. And your storage is again separated from compute. It is basically, there is a intelligent database storage engine that sits behind that, and that storage engine is the log processing system that I'm referring about, right? So basically, whatever data is written on your database or whatever database operation has been performed on your database, it gives it to the log processing system in form of log writes, and then that log processing system essentially writes that on a distributed file system in form of block storage, and this basically makes that operation much faster. It also has some inbuilt caches and analytics accelerators in place, and that is how it is able to deliver that high amount of performance than other standard offerings of the same database as such. And on top of that, as we were discussing, right, it has out of the box scalable compute, it has out of the box scalable storage which can horizontally scale on demand, and other than that, it has added ultra fast cache, and it stores data in mainly two formats, that is row format and columnar format. Now, a bit of a background, if let's say you want to do data processing operations in a very fast pace, right, like with analytics tools such as BigQuery and whatnot, all of these tools process your data in a columnar format where they store a combination of rows and columns in a specific format which is known as columnar format, and that format helps you in retrieving your data at a very fast pace or in a very short amount of time, right? And there is AIML driven auto columnarization feature within AlloyDB for PostgreSQL, where you just need to enable columnar engine, and it will basically detect your application, it will detect the operations that are going on between your application and your database, and it will intelligently determine which data it needs to organize and place in a columnar format so that it can be retrieved in a very short amount of time through your queries that application is interacting with your database. On top of that, it has inbuilt support with Vertex AI and other AIML offerings from Google Cloud, where you can create your ML models and functions and basically call them from within your database. Here's a very simple example, like if you want to build a fraud detection system, you can basically create and define these models and functions within Vertex AI and then call them directly from the database to invoke them, and then it would perform that relevant operation onto that specific object or entity. Some other features out of the box, since I mentioned it's a managed service offering, so you don't need to worry about scaling it, maintaining it on an ongoing basis, and you just have to like provision, specify the amount of capacity that you would like to have in the service, and then just let it be. It will automatically scale on an ongoing basis as data increases, as your traffic increases, and you don't need to worry about all those aspects behind the database. As we discussed, it is fully PostgreSQL compatible, so it has all the features. It supports all the triggers, functions that are available within PostgreSQL, and it is very nicely integrated with AI/ML services out of the box within the GCP landscape. So while we are discussing about database and modernizing your applications as such, here's a high-level view of various different database service offerings or data service offerings as such within Google Cloud. Starting from caches or in-memory store, we have memory store, that is basically a managed cache offering from Google Cloud. It is basically managed Redis and Memcache. You don't need to like install or manage it on your own. You can just switch on the service. It can get integrated with your database solution, and then you can start using it with your application as such. Then we have bare metal solution. This solution is more around procuring dedicated hardware and then migrating your Oracle workloads or such legacy workloads, which are very tightly coupled with specific licensing models, which cannot be directly migrated to a virtual machine as such. Then we have Cloud SQL, which basically supports 3 database engines as of now, that is MySQL, PostgreSQL, and Microsoft SQL Server. AlloyDB is the newest addition for PostgreSQL, which was recently released in Google I/O, and we have Cloud Spanner. Cloud Spanner is again a managed database offering from Google Cloud. Now, a major difference between Cloud SQL, AlloyDB, and Cloud Spanner is Cloud SQL basically uses the same engine that is available currently in the market, be it an open source engine or an enterprise engine like Microsoft SQL Server. It basically uses the same engine. You just have to specify the capacity that you would like to have. And again, it's a managed database offering on top of that particular engine. No other extra added features, no fine tuning on top of that or anything like that. AlloyDB, as we are discussing, is more for your enterprise grade top tier workloads where you need AI ML capabilities, you need fast query processing time, you need fast analytical time and whatnot. And Cloud Spanner is a database offering that can span across multiple regions. So if you are looking for, like, if you are just starting out building a small scale cloud native or digital native application within cloud, then you can go with Cloud Spanner because it's like a managed offering which is globally available, can span across multiple regions and support your workloads. But it is not fully compatible with the open source database engines that are available, right? It is SQL like, it has the relational database capabilities that are there, but it is like a wrapper on top of that sort of service. If you are starting out from scratch, it's probably the best option. But if you are migrating, it would require a bit of a replatforming as such on the application side or on the database side as such, right? So these are the major differences between these three database offerings, right? And on the other side, from NoSQL is kind of like very hot in market these days. People are leveraging NoSQL databases and document-based databases a lot for small scale applications as such, because it's very easy to scale, maintain. It provides a JSON-like schema, and it's basically schema-less, so it's easier to roll out new updates, build new features on top of that and whatnot. So we have two major offerings revolving around that. That is Cloud Firestore and Cloud Bigtable, right? And on top of that, for migration, so let's say like a lot of our customers are essentially interested in migrating from enterprises or licensed based databases to open source databases or to new cutting edge databases that are available, right? And like even from on-premise to cloud, but within the same database engine and whatnot, right? So for that, we have database migration service. It basically supports database migration from, let's say, on-prem to Google Cloud or from other cloud platforms to managed service of Google Cloud within either same engine or across multiple engines and whatnot. Oracle to Cloud SQL for Postgres was very recently launched. So basically, it provides capabilities to re-platform your Oracle database, migrate your schema from Oracle database to Cloud SQL for PostgreSQL, and re-platform your database on the go. So what are the different approaches on a high level to essentially modernize your enterprise grade applications, right? As I was mentioning, database migration service now supports Oracle to PostgreSQL schema and data migration for Cloud SQL for PostgreSQL. It's not yet released for AlloyDB for PostgreSQL, but that will also be down the line. Here are some of the reference architectures so as to how AlloyDB for Postgres is very seamlessly integratable with your existing application and with your existing workloads, right? So let's consider a scenario that you have a Java application which is currently running, let's say, on-premise, and it is already running with PostgreSQL on-premise or in some other cloud platform, and you'd like to migrate it to GCP, right? So you can basically leverage a mix of compute engine and AlloyDB, where your application can be migrated onto a series of compute engine instances which can sit under auto scaling with load balancing, with cloud storage for object storage and whatnot. And it can basically interact with the database that is in highly available mode on AlloyDB for PostgreSQL directly out of the box, because it supports all the connection parameters and configuration parameters that are there for any standard PostgreSQL database, right? You would not have to make any changes on your application side if it is already on PostgreSQL, right? And on top of that, you can leverage private service access, which is a private service offering from Google Cloud, where you can use your managed database services such as AlloyDB for PostgreSQL over a private channel or over a private network with the instances that are sitting within your VPC without exposing your database over the internet, right? So with PSA, with compute engine instances and load balancing, you can basically design a scalable architecture where you can run your applications on compute engine with AlloyDB for PostgreSQL. This is one such option, right? Now let's consider a scenario that your application is currently running on VMware and you would like to migrate it as is without making much changes as such on your application or without redesigning your architecture, right? So in this case, instead of using compute engine, you can just use Google Cloud VMware engine, which is a VMware service offering from Google Cloud. Rest of the architecture would essentially remain the same. You just have to replace the compute engine instances with VMware engine instances, and it would again get integrated with the AlloyDB for PostgreSQL or for any or with any other database service offering from Google Cloud as such. Another option, if let's say you have a digital native or a cloud native application which is already running on Docker, on containers, in any platform, let's say on premise or any other cloud platform as such, you can migrate your application onto Kubernetes, and then essentially using the same link that we saw earlier, that is over PSA, private service access, it can interact with the AlloyDB for PostgreSQL. No change in your application as such. It supports the standard configuration parameters that are there for PostgreSQL. And similarly, if let's say you don't want to manage any infrastructure by yourself, but your application is already containerized, you can move your application to a managed container platform on Google Cloud, that is Cloud Run. It basically provides very similar capabilities to GKE, but you don't need to manage the underneath cluster or any underneath infrastructure below that service. You just have to specify the vCPUs and memory that you need for your application. Just deploy your container, and it will take care of the rest, right? And over here, since we are running a managed database service offering, it would interact with that service offering using serverless VPC access, which allows serverless applications running on Cloud Run, Cloud Function, or any other serverless service for that matter, to interact with such managed VPC native services over a private link or over a private channel. Okay, so time for a quick demo. One another point to mention over here, AlloyDB for PostgreSQL is currently in public preview, and it is available at no cost within fair usage limit for quite some time before going into general availability. So feel free to play around with the service, explore the different features and offerings that are available within the same. Over here, we will just go ahead and try to create a very simple cluster and see how easy it is to get started within the console itself, right? So as you can see over here, you can choose what type of cluster you want to start with, like highly available or highly available with read pools, right? So read pools is again a very interesting concept that many of you might be aware about. Read pools or read replica, as you say, is basically a read copy of your database where you can divert your read traffic, right? So basically, whenever you are interacting with the database, you are performing two major operations on any transactional database as such. Either you are reading something or you are writing something, right? Now, if you have a single instance of that database, and if you are performing both the operations on that database, then it cannot serve your application in the most better way, right? So you can use the concept of read replica or read pool to diversify your traffic across multiple workloads. And basically what you can do is you can create a read replica or a read pool of your database where you can send all the read traffic to that specific endpoint, and all of your write traffic goes to the primary instance, right? So that way your users or your traffic or your queries get split across two different categories, and your system can scale and be maintained in a very efficient manner, right? So over here we will start with a highly available cluster, and you can always add as many read pools as you want later on going forward as well, right? We will just specify a sample cluster ID, GDG growth path, and I will just key in password. As you can see over here, it says PostgreSQL 14 is compatible. Storage, as we discussed, like it scales automatically. You don't need to specify it. It will automatically detect what amount of storage you are using currently, and then based on that, it will charge you according to the consumption. So there is no fear of over provisioning or provisioning in advance for the same, right? We will select the region. I will just keep it default for now. I will just select the default network that is available over here. And as you can see, since I have already configured it in the past, it shows that private services access connection is available over here, right? But if I would not have configured it in the past, it would ask me to create a private service access connection, which basically creates a VPC peering between the service producer VPC of this managed service and the VPC that exists within the Google Cloud where I am, where I like my service would be residing or where my application would be deployed essentially, right? So it performs a VPC peering between these two VPCs that exist within Google Cloud. And then I will hit continue. I will just give instance ID. And as you can see over here, we can specify what vCPU memory combination we want. These are the different combinations that are available out there. We can select any one of that, and then we can just go ahead and say create cluster, and it would automatically spin up a highly available cluster that is spread across multiple zones within the US Central 1 region within this particular network, and it will create a VPC peering with my network so that it is available over a private channel to my compute engine instances or to any of the VPC native services that are available within there, right? Now it takes a bit of time to create the cluster because, like I said, it spins up those compute resources within multiple regions, pairs them up with the storage that will go underneath that particular compute engine instances, and do all of that replication as such. As I said earlier, we can always add read pool instances, as many read pool instances as we want. So like, like a lot of our customers have business intelligence use cases where they want to like have a BI application or a data warehousing application that is sitting on premise to access these databases for some analytical or big data work use cases, right? So in those cases, they can just add as many read pool instances as they want and use those endpoints in their data warehousing applications or for their analytics use cases, right? So for the purpose of demo, I already have a sample database that is pinned up over here. So as you can see, it has all the monitoring dashboards populated over here where I can monitor my database performance over the period of time. We can even get query insights for more in-depth queries and performance and whatnot. And as you can see over here, there is one sample instance which is already available. And as you can see, there is a private IP address that is available for the primary instance that is there, right? Now, if I will add a read pool instance over here, in the similar manner, there will be another set of IP address that will be available for that read pool instance. And I can basically use separate endpoints for diversifying my traffic across the landscape, right? Now, let's see a very quick example of how we can connect to this database, let's say from an application, and how it can basically interact or get connected with your application as such, right? So I will go to compute engine, and I already have a demo instance deployed over here. So I will SSH real quick. Okay, it's establishing the connection and we are finally in. Okay, so as you can see over here, I have a sample demo application. It's basically a very simple Python application with a couple of configuration files that will just establish the connection with the database that already exists in AlloyDB, right? So if I will quickly show the database.ini file, as you can see, I've just specified the host, the database name, the user credentials of the database, and config.py basically parses this database.ini and loads the configuration parameters into an object that will be used by the connect.py file, right? Now, what this connect.py file does is it takes the configuration parameters from the object which read the database configuration parameters from the database.ini file and supplies that to the function which tries to establish a connection with the database. And once the connection has been established and it is able to find the supplier database within the database, it will just print the PostgreSQL version that it has been connected successfully on the terminal and whatnot, right? So let's go ahead and try to execute it. And as you can see over here, it is able to connect to the database. and it has printed like which database version is available within the database engine, and which operating system is powering that particular database engine, right? And as you can see, it says that it's PostgreSQL 14.2. Now let's say just for fun, if I will try and let's say change some parameter over here, like let's say replace the database name with Jimit, right? It would immediately throw the error that it is not able to connect to the database because the database does not exist in the first place, right? So as you can see, like I did not make any major changes as such to the original Python script or to the original Python application. It basically uses the same SDK as it would use for any PostgreSQL database wherever it is residing, right? It can basically use the same connection parameters, same methods that are used for connecting to the database and for performing any of the operations on the database and whatnot, right? So let me switch over to the production, to the presentation again. And that's pretty much it. I was not sure if the demo will go through and it will work, but yeah, that's pretty much it from my side. It's very easy to get started. Here's the link, cloud.google.com/AlloyDB, and I will open the floor for any questions.